Somewhere past the orbit of the outermost planet, the sunlight around you grows so faint that it stops behaving like daylight at all and starts behaving like something closer to starlight, scattered across an empty room. That transition is not gradual comfort fading into gentle dusk. It is a hard, physical shift, one that scientists have measured directly from spacecraft still transmitting data decades after launch. And it marks the first of many thresholds where space stops being merely empty and starts becoming actively hostile in ways most people never learn about in school. This is why the deeper you travel into the solar system and beyond, the more the universe reveals a side of itself that has nothing to do with the calm black backdrop we see in photographs, and everything to do with radiation that shreds unprotected tissue, cold that can freeze a body faster than any winter on Earth, and silences so complete that instruments built to detect the faintest signals still find nothing at all. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let us begin. The first place most people imagine when they picture leaving Earth is the Moon, and on the surface, it seems almost quaint compared to what waits further out. It is close. It is familiar. Apollo astronauts walked there and came home again. But the Moon is already a preview of a universe that does not forgive mistakes. It has no atmosphere at all, which means no protection from solar radiation, no protection from micrometeorites traveling faster than any bullet ever fired, and no way to spread heat evenly across its surface. During a lunar day, temperatures on the sunlit side climb past 120 degrees Celsius. During the long lunar night, the same ground plunges to nearly negative 170 degrees Celsius. A single lunar day lasts almost a full month, which means that swing between roasting and freezing happens slowly enough that there is no relief in either direction. Anyone standing on the surface without a suit would lose consciousness within about 15 seconds as the moisture in their lungs and on their eyes began to boil away in the vacuum, not because of heat, but because liquids boil at much lower temperatures when there is no air pressure holding them down. The body would not explode the way old films suggest. It would simply stop functioning very quickly, quietly, and without any of the drama fiction usually gives it. Radiation on the Moon is a separate and constant problem. Earth's magnetic field protects the surface below it from a storm of charged particles streaming from the sun and from deep space, but the Moon has no such shield. Astronauts on the surface absorb far higher doses of cosmic radiation than anyone on Earth ever does, and during a strong solar event, that dose can spike to levels that would cause serious harm within hours rather than years. The Apollo missions were, in a strange way, lucky. Between two of the missions, in the gap when no crew happened to be walking on the surface, instruments recorded a solar particle event so intense that had astronauts been outside their capsule at the time, the radiation dose could have been lethal. Nobody planned that gap. It was simply the schedule. And it is one of the quieter reminders that the difference between a historic moonwalk and a catastrophe can be a matter of timing that nobody controls. Micrometeorites complicate things further. Without an atmosphere to burn up incoming debris, even a fragment smaller than a grain of sand can strike the lunar surface at speeds exceeding 20 kilometers per second. At that velocity, the impact energy is enormous relative to the size of the object, capable of punching through a spacesuit or a spacecraft hull if the geometry is unlucky enough. Engineers design lunar habitats and suits with this constant hazard in mind, layering materials specifically to absorb and disperse the energy of impacts that happen far more often than most people realize, because there is no wind, no rain, and no erosion to slowly smooth away millions of years of cratering. Every scar on the lunar surface is permanent. The Moon does not heal, and yet, Of everywhere covered in this journey outward, the moon remains the gentlest stop. It is 3 days away by spacecraft. Rescue, in theory, is possible. Communication with Earth is instantaneous enough that a problem discovered can be discussed and addressed within seconds. The moon is dangerous, but it is dangerous in a way still tethered to home. Everything beyond it begins to sever that tether, one region at a time, and each severed connection makes the hazards not just more extreme, but more permanent. Traveling toward Mars means leaving the protective bubble of Earth's magnetosphere behind entirely, and that bubble does more work than most people appreciate. For the length of a Mars transit, which takes roughly 7 months, depending on the alignment of the planets, a crew would be exposed to the constant background hiss of galactic cosmic rays, particles accelerated to nearly the speed of light by exploding stars in other parts of the galaxy, long before our solar system even formed. These particles are not like the radiation from a medical scan. They carry so much energy that they pass through spacecraft hulls, through water shielding, and through the human body itself, breaking strands of genetic material as they go. Unlike solar radiation, which can be somewhat blocked with enough mass, galactic cosmic rays are so energetic that adding more shielding sometimes makes the problem worse, because the collisions create secondary particles, a spray of smaller fragments that can do just as much damage as the original ray. Studies using instruments aboard Mars-bound spacecraft have measured the radiation dose an unshielded traveler would absorb during a round-trip mission, and the number sits uncomfortably close to lifetime limits set for astronauts working in low Earth orbit across an entire career, except compressed into a single mission lasting under 2 years. Beyond the increased likelihood of cancer developing later in life, there are more immediate concerns. High doses of cosmic radiation have been linked in animal studies to changes in cognitive function, including memory difficulties and altered decision-making, raising uncomfortable questions about whether a crew making critical choices deep in interplanetary space might be operating with a brain subtly altered by the very environment they are traveling. Then there is the sun itself, which becomes a more erratic and more dangerous neighbor the farther a spacecraft drifts from Earth's shielding. Solar flares and coronal mass ejections release bursts of charged particles that can arrive at a spacecraft with very little warning, sometimes only tens of minutes between detection and impact. On Earth, these events produce auroras and, at worst, disrupt power grids and satellites. In deep space, with no atmosphere and no magnetic field standing between a traveler and the blast, an unshielded astronaut caught outside during a major solar event could receive a dose sufficient to cause severe radiation sickness within hours, with symptoms including nausea, vomiting, and a collapsing immune system. Spacecraft designers have responded by including small, shielded compartments, sometimes built from stored water or food supplies, that a crew could retreat into for the worst of an event. But even these shelters only reduce the dose. They do not eliminate it. Isolation compounds the physical danger. A radio signal from Mars orbit takes between roughly 4 and 24 minutes to reach Earth, depending on the relative positions of the two planets, and the same delay applies to the reply. That means a real-time conversation is impossible for most of the journey. Any emergency requiring guidance from mission control involves a built-in silence of many minutes on each end, a gap during which a crew must often act without confirmation, relying entirely on training and instinct rather than the immediate support that has always been available to astronauts working closer to home. Psychologists studying isolated environments, from Antarctic research stations to simulated Mars habitats, have documented a phenomenon sometimes called the third quarter effect, where morale and cohesion among a small, confined group tends to dip sharply somewhere past the midpoint of a long mission well before the relief of homecoming becomes close enough to feel real. Add genuine physical danger, permanent communication delay, and no possibility of an early return, and the psychological weight of interplanetary travel becomes a hazard every bit as real as the radiation itself. One that cannot be measured with a dosimeter, but shapes every decision a crew makes for months at a stretch. Mars itself does not offer relief once a spacecraft finally arrives. The planet has an atmosphere, but it is so thin, less than 1% the pressure of the air surrounding Earth, that it provides almost no protection from radiation and almost no insulation against temperature swings. A summer afternoon near the Martian equator might reach a mild 20 degrees Celsius, but the same location after sunset can fall past -70 degrees Celsius within hours, because there is not enough atmospheric mass to hold heat the way Earth's thicker air does. Without a pressurized suit, a person standing on the Martian surface would not freeze immediately, but they would lose consciousness within about 2 minutes, as the near-vacuum atmosphere pulled oxygen from their blood, a process functionally similar to what happens at extreme altitude on Earth, except with nowhere nearby to descend to for relief. The Martian surface itself carries a hazard that was not fully appreciated until robotic missions began analyzing the soil directly. Much of the fine dust covering the planet contains compounds called perchlorates, chemicals that are toxic to the human thyroid and nervous system in sufficient quantities. This dust is not confined to a few regions. It coats nearly the entire surface and gets lifted easily by the planet's frequent windstorms, some of which grow large enough to encircle the entire globe for weeks at a time, reducing visibility and cutting off the solar power that future habitats would likely depend on. Engineers designing surface habitats have had to account for filtration systems capable of keeping this toxic dust out of breathing air and off of any exposed skin. A level of contamination control most other planetary surfaces do not demand to nearly the same degree. Mars also lacks a global magnetic field, having lost whatever internal dynamo once generated 1 billions of years in the past. Without that field, the solar wind has been slowly stripping away the planet's original atmosphere for eons, which is part of why Mars ended up so thin and cold in the first place. For anyone living there long term, this means the same cosmic and solar radiation hazards present during the journey never really end once you arrive. Radiation detectors placed on the surface by robotic landers have recorded steady background doses roughly comparable to what a crew experiences during transit, meaning a colonist on Mars accumulates radiation exposure every single day of their life there, with no month ever offering a meaningful reprieve the way a shielded room on Earth would. Then there is the matter of gravity itself, which on Mars sits at roughly 38% of what a human body evolved to expect. Studies of astronauts returning from long stays in the reduced gravity of orbit have documented bone density loss, muscle atrophy, and changes to eyesight caused by fluid shifting differently inside the skull. Scientists do not yet know with certainty what decades spent at Martian gravity would do to a human body, or to a child born and raised there who never experienced Earth's full pull at all. It is possible such a person would never be able to visit Earth safely. Their skeleton and cardiovascular system adapted permanently to a lighter world, making a return to full gravity potentially harmful rather than simply uncomfortable. The farther this hypothetical colonist strays from Earth, the more their own biology begins to diverge from the species they descended from, a slow and largely invisible transformation driven entirely by the physics of the world they now call home. Beyond Mars lies the asteroid belt, a region that popular fiction has trained most people to imagine as a chaotic obstacle course of tumbling rocks, packed so densely that a ship would need to weave constantly to avoid collision. The reality is almost the opposite, and in its own way, that reality is more unsettling. The asteroid belt is so vast, and its contents so sparsely distributed, that the average distance between any two sizable objects is measured in millions of kilometers. A spacecraft could cross the entire belt without ever coming close enough to see a single asteroid with the naked eye. There is no crowded rock field. There is only emptiness punctuated by the occasional distant speck of rubble, and that emptiness is precisely what makes the region unnerving once you understand it correctly. It is not dangerous because it is crowded. It is dangerous because it is so silent and so seemingly empty that a traveler could begin to feel as though they have left the solar system entirely, adrift in a nothing so complete it plays tricks on the mind. The asteroids themselves, when you do encounter one, are not the smooth boulders often depicted on screen. Many are loosely bound piles of rubble held together by little more than their own weak gravity, a structure scientists call a rubble pile. Landing on such a body means dealing with gravity so faint that a poorly timed footstep could launch a person into a slow, tumbling escape from the surface entirely, drifting away into space with no way to push back against nothing. Some smaller asteroids have gravity so weak that dropping an object from head height would take it several minutes to reach the ground, and a person jumping even slightly too hard could achieve escape velocity from the entire body without meaning to. Astronauts training for hypothetical asteroid missions have had to learn entirely new movement techniques, closer to careful, deliberate handholds than the confident walking most people associate with any planetary surface. The composition of individual asteroids varies enormously and carries its own dangers. Some are rich in metal, dense chunks of nickel and iron left over from the shattered cores of protoplanets that never fully formed. Others are loose aggregates of ice and carbon-rich material, barely holding together at all. Spacecraft approaching an unfamiliar asteroid often cannot know in advance which type they are dealing with, and the difference matters enormously for anchoring, drilling, or simply standing on the surface without triggering a small landslide in near-zero gravity, where even minor disturbances can send debris drifting outward in slow, silent clouds that take a surprisingly long time to settle. Radiation exposure in the belt remains just as severe as anywhere else this far from Earth's shielding, and the psychological toll of the region may be its most underappreciated hazard. A traveler moving through the belt sees no crowded rocks, no dramatic near misses, nothing resembling the exciting chaos of fiction. They see mostly stars, a shrinking sun, and long stretches where even the belt's largest residents, bodies such as Ceres or Vesta, remain too far away to be visible without a telescope. That prolonged, featureless emptiness, stretched across months of travel, has been cited by mission planners as a genuine psychological concern, distinct from the fear of collision entirely. The asteroid belt teaches an early and important lesson about deep space that only grows more true the farther out you travel. The danger out here is rarely a dramatic impact. It is far more often the crushing, patient weight of emptiness itself. Push further outward, past the asteroid belt, and the solar system's character changes entirely once you reach the domain of the gas giants. Jupiter is the first and, in many ways, the most openly hostile of the planets. It has no solid surface to speak of, only layers of hydrogen and helium that grow denser and hotter the deeper you descend, transitioning gradually from gas to a strange fluid state, and eventually to metallic hydrogen, under pressures so extreme that the physics stops behaving like anything encountered on Earth. There is no landing on Jupiter in any meaningful sense. A spacecraft attempting to descend would be crushed, heated, and torn apart by increasingly ferocious winds long before reaching anything resembling solid ground, because no solid ground exists to reach. Jupiter's radiation environment is, on its own, one of the most dangerous regions in the entire solar system. The planet's magnetic field is enormously more powerful than Earth's, and it traps charged particles into belts that surround the planet at levels of intensity capable of destroying unshielded electronics within hours and delivering a lethal dose of radiation to an unprotected human within minutes. Spacecraft sent to study the Jovian system are engineered with radiation vaults, thick-walled compartments built specifically to protect sensitive instruments from an environment so harsh that mission planners must carefully choreograph orbital paths to minimize time spent in the most intense radiation zones, threading a narrow path through belts of charged particles that would otherwise cook their electronics within a single close pass. The moons orbiting Jupiter carry their own distinct dangers layered on top of this radiation problem. Europa, an icy moon believed to hide a liquid ocean beneath its frozen crust, sits deep inside Jupiter's radiation belts, meaning any future mission to its surface would need shielding robust enough to protect both instruments, any human crew from a bombardment of charged particles constant enough to be measured in a dangerous dose within a matter of days rather than years. Io, the innermost of the large moons, presents an entirely different hazard. It is the most volcanically active body known in the solar system. Its surface constantly reshaped by eruptions, driven by the intense tidal flexing caused by Jupiter's gravity, pulling and releasing the moon with every orbit. Lava flows on, Io can stretch for hundreds of kilometers, and volcanic plumes have been observed launching material hundreds of kilometers above the surface, some of which escapes the moon entirely and feeds a torus of charged particles that further intensifies Jupiter's already dangerous radiation belts. Saturn, further out still, trades Jupiter's raw radiation intensity for a different kind of hazard built from scale and cold. Its rings, breathtaking from a distance, are in fact composed of countless individual particles of ice and rock, ranging from dust-sized grains to chunks larger than a house, all orbiting at different speeds and in slightly different planes. A spacecraft attempting to cross the ring plane at the wrong angle risks a collision with debris traveling at velocities high enough to shatter a hull instantly. And mission planners studying the region have had to calculate approach trajectories with extreme precision, specifically to avoid this danger. Saturn's moon, Titan, offers something almost inviting by comparison, a thick atmosphere and lakes of liquid on its surface. But those lakes are not water. They are methane and ethane, chilled to roughly -180 degrees Celsius, cold enough that any human exposure without heavy insulation would cause severe frostbite within seconds and full body freezing shortly after. The farther out among these giants you travel, the more clearly a pattern emerges. Every world grows more visually spectacular and simultaneously more lethal, as though the solar system saves its most beautiful sights for its most unforgiving neighborhoods. Beyond Saturn, Uranus, and Neptune wait in a region so far from the sun that daylight, there is little more than a dim twilight, roughly 400 times fainter than what reaches Earth. These ice giants are colder still than anything encountered so far, with cloud-top temperatures on Neptune plunging to roughly -200 degrees Celsius. Neptune is also home to the fastest winds ever recorded on any planet in the solar system. Storms that howl at speeds exceeding 2,000 kilometers per hour, fast enough to circle the entire planet in under a day. Nothing on Earth compares to this kind of atmospheric violence, and any hypothetical descent through Neptune's atmosphere would subject a spacecraft to forces far beyond anything engineered structures have ever been tested against. Uranus adds its own strange twist to the hazards of this region, tilted on its side so severely that its poles take turns facing the sun directly for decades at a time, followed by decades of near total darkness. A traveler arriving during the depths of a Uranian polar night would find a world where the faint, distant sun never rises at all for years on end, plunging any surface installation into a darkness broken only by starlight and the pale glow of the planet's faint ring system. This is deep space beginning to intrude on the solar system itself, an environment where the sun stops functioning as a meaningful source of daylight and becomes instead simply the brightest point of light in an otherwise black sky. A transition that becomes total and permanent once you travel further still into the Kuiper Belt. The Kuiper Belt begins roughly at Neptune's orbit and stretches outward into a region containing countless icy bodies, including the dwarf planet Pluto, left over from the formation of the solar system billions of years ago. Out here, the sun has shrunk to something that resembles a very bright star rather than a source of warmth, delivering so little energy that surface temperatures on Kuiper Belt objects hover consistently near -230 degrees Celsius, only a handful of degrees above absolute zero, the theoretical point at which all molecular motion stops entirely. At these temperatures, common substances behave in ways utterly foreign to human experience. Nitrogen, which exists as an invisible gas making up most of Earth's atmosphere, freezes solid on Pluto's surface, forming glaciers of frozen nitrogen ice that slowly flow across the dwarf planet in patterns strikingly similar to glacial ice on Earth, despite being made of an entirely different material, behaving in an entirely different temperature regime. Communication delays in this region stretch to a point where the very idea of remote operation becomes almost meaningless. A radio signal sent from Pluto takes more than 5 hours to reach Earth, meaning any command sent to a spacecraft here and any reply confirming it was received involves a round-trip conversation lasting the better part of a working day. There is no possibility of joystick-style control at this distance. Every spacecraft operating in the Kuiper Belt must function largely autonomously, making its own decisions about hazards and course corrections, because human oversight, while still technically possible, has become so slow that it is functionally useless for anything requiring a quick response. This is the point in the outward journey where the solar system itself begins to feel less like a neighborhood and more like the edge of something far larger and far less forgiving. Further out still lies the Oort cloud, a theorized shell of icy bodies believed to surround the entire solar system, at a distance so extreme that light from the sun takes the better part of a year to cross it. Nobody has ever directly photographed an Oort cloud object up close. Its existence is inferred from the orbits of long-period comets, icy wanderers that occasionally fall inward toward the sun on journeys lasting thousands or even millions of years before returning to the deep cold from which they came. If a spacecraft could somehow reach the inner edge of this region, the sun would have dimmed to something almost indistinguishable from any other star in the sky, a faint point of light, providing essentially no usable warmth or illumination at all. This is the moment where the concept of daytime stops applying entirely, replaced by a permanent starlit dark that stretches in every direction without end. The isolation at this distance becomes almost impossible to describe in human terms. A radio message sent from the outer edge of the Oort cloud would take more than a year to reach Earth, and a reply would take another year to return, meaning any conversation with mission control would unfold across a delay longer than most people's memory of recent events. A traveler stranded out here experiencing any kind of emergency would, for all practical purposes, be entirely on their own, with no possibility of assistance arriving in any time frame that could matter. This is not simply distance in the way Mars or even the Kuiper Belt represents distance. This is a scale where the very idea of rescue collapses into something closer to a philosophical question than a practical one. Temperatures in this region sit only a few degrees above absolute zero, close enough to the theoretical floor of coldness that the distinction becomes largely academic. At these temperatures, materials behave in ways that defy ordinary intuition. Metals become brittle enough to shatter under stresses they would easily absorb at room temperature. Lubricants freeze solid, seizing mechanical components that rely on smooth movement. Even the simplest maintenance task, the kind an engineer on Earth might complete in minutes, becomes a serious engineering challenge when every material involved is behaving according to the strange rules of extreme cryogenic conditions. Any hypothetical outpost built this far from the sun would need to generate every joule of its own heat and light internally, entirely disconnected from any external energy source. A level of self-sufficiency far beyond anything humanity has ever attempted to sustain. And yet, even the outer edge of the Oort cloud, as remote and cold and dark as it is, remains gravitationally bound to the sun. It is still, technically, part of our solar system, the true boundary, the point where the sun's gravitational influence finally yields entirely to the pull of neighboring stars, and the broader structure of the galaxy lies still further beyond, marking the true threshold into interstellar space, a realm where the physical dangers already described begin to feel almost quaint compared to what waits on the other side. Crossing into true interstellar space means leaving the protective bubble the sun creates around itself, a region called the heliosphere, formed by the constant outward pressure of the solar wind pushing back against the thin gas and dust drifting between the stars. Two spacecraft, launched in the 1970s and still transmitting data decades later, have actually crossed this boundary, and the readings they sent back revealed something scientists had not fully expected. Just outside the heliosphere, the density of surrounding material spikes noticeably, while the intensity of galactic cosmic rays increases sharply, confirming that the sun's magnetic bubble had, in fact, been shielding the inner solar system from a much harsher radiation environment all along. Once a spacecraft leaves that bubble behind, it is bathed constantly in the unfiltered radiation of the galaxy itself, with no planetary magnetic field, no atmosphere, and no solar wind to soften the exposure in any way. The interstellar medium, the thin gas and dust that fills the space between stars, is not empty in the way many people imagine. It contains scattered hydrogen and helium atoms, along with heavier elements forged inside long-vanished stars and scattered outward when those stars ended their lives in explosive fashion. The density out here is almost impossibly low compared to anything on Earth, often just a handful of atoms per cubic centimeter, yet even this near vacuum carries consequences for anything moving through it at high speed. A spacecraft traveling toward another star system at any meaningful fraction of the speed of light would encounter these scattered atoms as a kind of radiation hazard in their own right, since even a single hydrogen nucleus striking a hull at a significant percentage of light speed carries enough energy to behave almost like a tiny bullet, and encountering enough of them over the course of a journey lasting years or decades would gradually erode any unshielded surface. Distances between stars at this stage of the journey stop making intuitive sense entirely. The nearest star system to our own sun lies roughly 4.24 light-years away, a distance so large that even traveling at speeds far beyond anything humanity has ever achieved with a spacecraft, the journey would still stretch across many decades or centuries. Voyager, the farthest traveling spacecraft humanity has ever launched, moving at tens of thousands of kilometers per hour, would still need tens of thousands of years to cover that distance, despite already having spent decades in flight and already having crossed into true interstellar space. Out here, The concept of a return trip becomes essentially meaningless. Any crew embarking on such a journey would be committing not just themselves, but likely several future generations to a life lived entirely within the confines of a moving vessel, disconnected from Earth in every practical sense. Their only contact with home, a radio signal stretched across a delay measured in years, and eventually decades, as the distance continued growing. The isolation here is not merely physical. It becomes cultural and generational. A crew born aboard such a ship, living and growing old without ever seeing Earth, would have no direct experience of the world their ancestors left behind, inheriting only stories, recordings, and increasingly abstract cultural memories of a planet that continues changing without them while they remain frozen, in a sense, inside the values and knowledge of the era their journey began. Some researchers, studying the psychology and sociology of hypothetical generation ships, have raised serious concerns about whether human culture and cooperation could remain stable across such a multi-generational voyage, isolated entirely from the broader human population, with no possibility of fresh perspectives or outside contact arriving to relieve the pressures that build naturally within any small, closed community forced to depend entirely on itself for everything. Reaching another star system does not offer the relief a traveler might hope for after such an enormous journey. The nearest star to our own is actually part of a triple system, and orbiting one of its 3 stars is a rocky planet sitting within a zone where liquid water could theoretically exist. On paper, this sounds promising. In practice, the star it orbits closely is a small, dim, and violently active type known as a red dwarf, a category of star that makes up the majority of all stars in the galaxy, but behaves nothing like our own sun. Red dwarfs are prone to sudden, ferocious flares that can briefly outshine the star's normal brightness by a significant multiple, blasting any orbiting planet with radiation and charged particles intense enough to strip away an atmosphere over time, if the planet lacks a sufficiently strong magnetic field of its own. Planets orbiting close enough to a red dwarf to receive enough warmth for liquid water often end up tidally locked, meaning the same side of the planet always faces its star, just as the same side of the moon always faces Earth. This creates a world with one permanent day side, baked under constant starlight, and one permanent night side, locked in eternal darkness and cold. Between these two extremes lies a narrow twilight band, where temperatures might theoretically balance out enough to support liquid water, but the atmospheric dynamics required to sustain such a delicate balance remain deeply uncertain, and many models suggest that violent winds constantly tearing between the hot and cold hemispheres could make the environment far more chaotic than the calm, temperate strip such worlds are sometimes imagined to have. Even setting aside these environmental hazards, arriving at another star system means confronting a new and profound kind of unknown. Every hazard described so far in this journey, from lunar vacuum to interstellar radiation, involves environments scientists have measured directly, using data returned from robotic missions or instruments here on Earth. A newly reached exoplanet offers no such certainty. Its atmospheric composition, its surface chemistry, its potential for hosting anything resembling life, all of it would need to be studied, essentially from scratch upon arrival. With no ability to consult decades of prior research the way missions to Mars or Jupiter can, any life encountered there, should it exist at all, would have evolved under an entirely separate set of pressures, with no guarantee that its biochemistry would be compatible with, or even comprehensible to, anything humans understand about biology. There is also the unsettling possibility that the system contains nothing at all worth the journey. A genuine risk, given how difficult it remains to determine a planet's habitability from light years away, using only the light that reaches our telescopes. Astronomers have already catalogued numerous exoplanets that initially appeared promising in early observations, only for more detailed follow-up study to reveal crushing atmospheric pressures, toxic chemical compositions, or surface conditions closer to a furnace than anything resembling a garden. A civilization committing generations of resources and human lives to reach a distant star system would be doing so with incomplete information, accepting a real possibility that the destination itself might offer little more than another lifeless, hostile rock, indistinguishable in its hazards from anywhere already passed through on the long journey outward. Zoom out from any single star system, and the true scale of the galaxy begins to reveal a different category of horror entirely. One built not from cold or radiation alone, but from gravity, behaving in ways that break the ordinary rules of physics. At the center of the Milky Way lies a supermassive black hole named Sagittarius A, an object with a mass equivalent to roughly 4 million suns compressed into a region smaller than the orbit of Mercury around our own star. Nothing, not light, not matter, not information of any kind, escapes once it crosses the boundary surrounding this object, known as the event horizon. Stars near the galactic center have been observed whipping around Sagittarius A at speeds reaching a significant fraction of the speed of light, tracing orbits so tight and so fast that astronomers have used them to directly confirm the black hole's staggering mass through decades of careful, patient observation. Approaching a black hole closely enough introduces a hazard unlike anything encountered elsewhere on this journey, a phenomenon researchers call spaghettification. As an object falls toward a black hole, the gravitational pull on the near side becomes significantly stronger than the pull on the far side, because the near side is simply that much closer to the source of the gravity. For a supermassive black hole like Sagittarius A, this difference remains gentle enough for quite a while during the approach, meaning a traveler could, in theory, survive falling toward the event horizon far longer than they could near a smaller black hole, where the tidal forces grow lethal at a much greater distance. But eventually, close enough to any black hole, that difference in pull becomes extreme enough to stretch an object first gently, then violently, elongating it along the direction of the fall, until whatever structure it once had can no longer hold together at all. Even without approaching a black hole directly, the galactic center is an extraordinarily hostile neighborhood. The density of stars near Sagittarius A is enormously higher than anywhere in our own comfortable corner of the galaxy, meaning close stellar encounters and the resulting gravitational chaos happen far more frequently. Some of these stars are young, hot, and short-lived, ending their existence in supernova explosions that blast intense radiation across surrounding space. A planet orbiting anywhere near the galactic center would face a background radiation environment far harsher than anything experienced in our own relatively quiet galactic suburb. One reason many astronomers consider regions closer to galactic centers, ours included, to be far less favorable for the long-term stability life seems to require. The space between stars near the galactic core is also filled with dense clouds of gas and dust, some of it swirling into an accretion disk around Sagittarius A itself, heated to enormous temperatures as friction and gravity compress the material before it eventually falls past the event horizon. This disk emits intense radiation across the electromagnetic spectrum, including bursts of high-energy particles that occasionally erupt outward in dramatic flares. Astronomers have observed directly using instruments sensitive to exactly this kind of emission. A traveler journeying toward the heart of our own galaxy would be moving toward an environment defined by extremes at every scale: extreme density, extreme radiation, extreme gravity, and ultimately an object so powerful that it can erase anything, crossing too close to it from the observable universe entirely, with no signal, no light, and no information ever escaping to confirm what happened. Leave the Milky Way entirely, and the journey enters a scale so vast that individual stars stop being a meaningful unit of measurement at all. The distance between our galaxy and its nearest large neighbor spans roughly 2.5 million light-years, a gap so enormous that light itself, the fastest thing in existence, takes millions of years to cross it. A traveler moving through this intergalactic space would find themselves in an environment even emptier than anything encountered inside a galaxy, since the space between galaxies contains, on average, only a tiny fraction of the matter density found even within the sparse asteroid belt or interstellar medium described earlier in this journey. Out here, gravity from any single object becomes almost irrelevant across such enormous distances, and the sky itself would look profoundly different from anything familiar, with our own galaxy shrinking into a faint smudge of light and eventually vanishing entirely as the distance grew large enough. This region is not without structure, however, and the structure it does have is unsettling once properly understood. Galaxies are not scattered randomly through the universe. They cluster together along vast filaments of matter, forming a cosmic web with enormous, largely empty voids stretched between the strands. Some of these voids span hundreds of millions of light-years across, containing only a scattering of isolated galaxies drifting through an otherwise near total emptiness. Astronomers have discovered that our own galaxy sits at the edge of just such a structure, a region measurably less dense than the cosmic average, meaning the emptiness surrounding us is not merely a hypothetical destination for some future journey. It is, in a very real sense, already our neighborhood, stretching outward in every direction we can observe. Traveling deep into one of these cosmic voids means confronting an environment where the sky, over time, would darken far beyond anything a traveler had experienced before, not because of any nearby obstruction, but simply because there is almost nothing left nearby to reflect or emit light at all. Distant galaxies would remain visible only as extraordinarily faint smudges, and eventually only through the sensitivity of specialized instruments rather than anything resembling ordinary sight. Time itself would seem to stretch in an unsettling way here too, since any communication attempting to reach a distant galactic civilization, should one exist, would face delays measured not in years or decades but in millions of years. A timescale so far removed from any human institution or lifetime that meaningful two-way contact becomes essentially a mathematical impossibility rather than merely an engineering challenge. Perhaps most unsettling of all is what these vast cosmic voids reveal about our own understanding of the universe. Regions this empty do not form easily according to standard models of how matter distributed itself following the earliest moments after the Big Bang, and their existence has forced cosmologists to reconsider assumptions about how uniform the universe truly is on the largest scales. A traveler who journeyed deep into one of these voids and attempted to measure the expansion of the universe from within, it would likely calculate a different rate than an observer positioned inside a dense cluster of galaxies, since the gravitational pull from surrounding dense regions subtly warps the local expansion in ways scientists are still working to fully understand. The farther this journey travels, the less the universe resembles a stable, measurable backdrop, and the more it reveals itself as something whose basic properties shift depending on exactly where, within its vast structure, you happen to be standing. Push the journey further still, toward the very edge of what can ever be observed, and the horror shifts from something physical into something closer to a fundamental limit built into the structure of reality itself. The universe has been expanding since its earliest moments, and that expansion has been accelerating for the past several billion years. Driven by a mysterious pressure scientists call dark energy, something whose true nature remains one of the largest unsolved questions in all of physics. Because of this accelerating expansion, there exists a boundary beyond which light from a galaxy will never be able to reach us, no matter how much time passes. Galaxies beyond that boundary are not simply far away. They are permanently, irrevocably cut off, receding from us faster than light itself can close the growing gap between us. This means that at this very moment, countless galaxies exist whose light will never arrive here, no matter how long humanity, or whatever eventually succeeds humanity, continues to watch the sky. Some of these galaxies may already be gone in the sense that they existed briefly and evolved and changed long ago, and we will simply never know because the information describing what happened to them is permanently beyond our reach, swallowed by the expanding gap of space itself rather than by any black hole or physical barrier. A traveler pushing outward toward this cosmic horizon would be moving toward a boundary that recedes just as fast as they approach it, an infinite journey toward a destination that can never actually be reached. Since the very act of traveling that direction does nothing to close a gap being stretched open by the expansion of space itself, faster than any spacecraft could ever hope to counter. This accelerating expansion carries an implication far larger than any single traveler's journey. Over sufficiently long timescales, stretching not merely millions but trillions of years into the future, distant galaxies will continue receding until eventually every galaxy outside our own immediate local group disappears entirely from view, stretched beyond the cosmic horizon and lost forever. A civilization arising in the unimaginably distant future, long after this process completes, would look out at what remained of the night sky and see almost nothing at all beyond their own galaxy, with no way of ever discovering that a vast universe, full of countless other galaxies, once existed and was, in principle, observable. They would have no evidence the Big Bang ever happened, no observable cosmic microwave background, and no way to reconstruct the true scale or history of the cosmos they were born into. They would simply be wrong about the universe, in ways so complete and so undetectable that no future observation could ever correct the mistake. This is, in its own way, one of the deepest and least discussed horrors this entire journey has to offer. It is not built from cold, or radiation, or crushing gravity, though all of those remain real and present at every scale examined so far. It is built from the simple, unsettling fact that the universe is actively erasing its own evidence of itself, continuously and irreversibly, and that whatever understanding any civilization manages to build about the cosmos is only possible because that civilization happens to exist during a narrow and temporary window, when enough of that evidence still remains visible. Travel far enough, in either distance or time, and eventually the universe stops being knowable at all, not because anything prevents the observation directly, but because the very thing being observed has already slipped permanently beyond reach. Even setting aside black holes, the graveyard of the galaxy contains other objects whose physical extremity rivals anything discussed so far. Neutron stars, the collapsed remnants left behind after a massive star ends its life in a supernova explosion, pack a mass greater than our own sun into a sphere often no larger than a modest-sized city. The density inside such an object is so extreme that a single teaspoon of its material would weigh roughly as much as a mountain here on Earth. Gravity at the surface of a neutron star is billions of times stronger than gravity on Earth. Strong enough that an object dropped from just a meter above the surface would strike with an impact, releasing energy comparable to a large explosive detonation, simply from the acceleration gained during that short fall. Many neutron stars also rotate at astonishing speeds, some completing hundreds of full rotations every single second, a rate so fast it seems to defy the basic intuition of how a solid object should behave without tearing itself apart. These rapidly spinning neutron stars, known as pulsars, sweep intense beams of radiation across space with each rotation. Beams so precisely regular that early astronomers briefly wondered whether they had detected an artificial signal from an intelligent civilization before understanding the true, entirely natural cause. A traveler passing near enough to a neutron star's beam would be exposed to a blast of radiation intense enough to be immediately and thoroughly harmful, arriving with a regularity as predictable and inescapable as the ticking of some enormous, indifferent cosmic clock. Some neutron stars possess magnetic fields so powerful that scientists have given them their own separate name, magnetars, and their fields are strong enough to distort matter at the atomic level from a considerable distance away. A magnetar's magnetic field is intense enough that, according to calculations published by astrophysicists studying these objects, it could theoretically disrupt the chemical bonds holding ordinary molecules together in a human body from thousands of kilometers away, rearranging the very shape of atoms before any other hazard even had the chance to matter. In 2004, astronomers recorded a burst of energy from a magnetar so powerful that it measurably disturbed the upper layers of Earth's own atmosphere, despite originating from a source tens of thousands of light-years away. A vivid demonstration of just how much destructive energy these compact, silent objects are capable of releasing in a single burst lasting only a fraction of a second. Occasionally, two neutron stars or black holes locked in orbit around each other will spiral inward and finally merge, an event so violent it briefly outshines entire galaxies in certain forms of radiation and sends ripples through the fabric of space-time itself. Detected here on Earth as gravitational waves by instruments sensitive enough to measure a distortion in space thousands of times smaller than the width of a single proton. These merger events also forge many of the heaviest elements in the universe, scattering freshly created gold, platinum, and other heavy metals outward into space in a violent explosion of debris. It is a strange and almost poetic detail that some of the very atoms making up jewelry or electronics here on Earth were likely created in exactly this kind of cataclysmic, extraordinarily distant event. A reminder that even the material comforts of ordinary life trace their origin back to some of the most violent processes the universe is capable of producing. Between these dramatic, well-studied objects drifts something far quieter and, in its own understated way, just as troubling. Astronomers have discovered that the galaxy likely contains an enormous population of rogue planets, worlds ejected from their original star systems by gravitational encounters with other planets or passing stars, now drifting alone through interstellar space with no star to orbit at all. Some estimates suggest there could be more rogue planets wandering the galaxy than there are stars to host planetary systems in the first place. A staggering number of worlds falling through permanent darkness, forever cut off from any source of warmth or light beyond the faint background glow of distant stars scattered across the sky. A rogue planet with a solid surface would exist in a state of permanent, absolute cold, since its only possible source of internal warmth would come from radioactive decay deep within its core or from residual heat left over from its formation billions of years earlier. both of which are far too weak to meaningfully warm a surface exposed to the near absolute zero temperature of open space. Any liquid water once present on such a world would have frozen solid to a depth of many kilometers long ago, though some scientists have speculated that certain rogue planets might retain a liquid ocean deep beneath a thick ice shell, kept warm not by any star but by internal geological heat, similar in principle to the subsurface oceans suspected beneath the icy moons of Jupiter and Saturn, discussed earlier in this journey. If life exists on such a world, it would be entirely and permanently isolated from starlight, evolving in complete darkness across geological timescales with no concept of day, night, or season ever developing at all. Detecting these wandering worlds from Earth is extraordinarily difficult, precisely because they emit almost no light of their own and reflect no sunlight, since they orbit no sun to reflect light from in the first place. Astronomers have only managed to identify a relatively small number of confirmed rogue planets so far, using a technique called gravitational microlensing, which detects the subtle bending of light from a distant background star as an invisible, unlit planet happens to pass directly between that star and Earth's telescopes. The rarity of these precise alignments means that the vast majority of rogue planets almost certainly pass entirely undetected, drifting silently through the galaxy in numbers far exceeding anything astronomers have directly confirmed. An invisible population of dark, frozen worlds occupying the seemingly empty spaces between the stars we can actually see. A traveler crossing interstellar space over sufficiently long distances would, statistically, eventually pass reasonably close to one of these wandering worlds, drifting alone with no star of its own, its surface locked in permanent darkness and cold, far more absolute than anything experienced even in the depths of the Kuiper Belt or Oort cloud earlier in this journey. There would be no warning of its approach, since it emits no light and reflects nothing to be seen from a distance, and a spacecraft's instruments might only detect its presence through the subtle gravitational pull it exerts on nearby objects. A silent, invisible mass drifting through the dark, indifferent to whatever else happens to be sharing the same patch of empty space at the same moment. Any serious discussion of traveling truly vast distances eventually runs into a hazard that has nothing to do with radiation, cold, or gravity, and everything to do with the fundamental structure of time itself. According to the theory of relativity, confirmed through more than a century of precise experimental testing, time does not pass at the same rate for everyone. It slows down for an object moving at a significant fraction of the speed of light, relative to someone who remains still. A crew traveling toward a distant star system at close to light speed would, from their own perspective, experience the journey as relatively brief, perhaps only a handful of years passing aboard their ship. Back on Earth, however, decades or even centuries could pass during that same span, an effect that has been measured directly, though far more subtly, using extremely precise atomic clocks flown aboard ordinary aircraft here on our own planet. The implications of this effect become genuinely unsettling once applied to interstellar travel at meaningful fractions of light speed. A crew returning from even a modest relativistic journey might find that everyone they once knew has grown old or passed on entirely during their absence, that the culture and technology of Earth has changed beyond easy recognition, and that the civilization they return to bears little resemblance to the one they departed from. In a very real sense, traveling far enough and fast enough functions as a one-way trip, not merely through space, but through time itself, severing a traveler from their own era, just as thoroughly as physical distance severs them from their own planet. There would be no true homecoming waiting at the end of such a journey, only arrival in a future that has continued moving forward without them. Achieving speeds anywhere close to a significant fraction of light speed, introduces its own additional dangers, layered directly on top of this time distortion. At such velocities, even the thin interstellar medium discussed earlier stops behaving like a harmless near vacuum and starts behaving like a hazardous, abrasive environment, since every stray hydrogen atom or dust particle a ship encounters carries enormous kinetic energy purely as a consequence of the ship's own extreme speed relative to it. Engineers studying hypothetical relativistic spacecraft design have proposed shielding systems built specifically to vaporize or deflect these particles before they strike anything critical. But no design yet exists that could guarantee complete protection across a journey lasting years while moving at such extreme velocity, meaning even successfully surviving the trip itself remains a serious, unsolved engineering problem rather than a straightforward application of known technology. There is also a subtler danger buried in this relativistic framework, one that speaks to just how strange traveling far enough into the universe eventually becomes. As an object approaches the speed of light, the energy required to accelerate it further increases without any theoretical limit, meaning that reaching light speed itself, rather than merely approaching it closely, would require an infinite amount of energy, a threshold no physical process is understood to be capable of crossing. This is not an engineering limitation that better technology might someday overcome. It is a fundamental boundary built into the structure of the universe itself. One more example of how traveling far enough eventually reveals not simply more distance to cross, but hard limits on what is physically possible to accomplish at all, no matter how advanced a civilization attempting the journey might become. Push the timescale of this journey forward rather than merely the distance, and an entirely new category of horror emerges, one that awaits not some distant region of space but the universe as a whole. Stars do not burn forever. Even the longest lived among them, small, dim red dwarfs that burn their fuel with extraordinary efficiency, are expected to continue shining for trillions of years, but eventually, every star will exhaust its usable fuel. Our own sun will expand into a bloated giant star in roughly 5 billion years, likely engulfing the inner planets before eventually shedding its outer layers and collapsing into a small, dense remnant called a white dwarf, which will then cool slowly over an almost incomprehensible span of time, fading gradually from a hot ember into something scientists have named a black dwarf, an object so cold and dark it emits essentially no detectable light or heat at all. No black dwarf has ever actually been observed, and none ever will be, at least not by anything resembling current human civilization, because the universe is not yet old enough for any star to have completed this cooling process. Calculations suggest reaching this final, frozen stage requires a length of time so vast that expressing it meaningfully becomes difficult, even using scientific notation, a span of time so many multiples longer than the current age of the universe that comparing the two feels almost meaningless, like comparing a single heartbeat to the entire span of geological history. Long before any black dwarfs finish forming, star formation itself across the universe will have slowed dramatically and eventually stopped almost entirely. As the raw hydrogen gas needed to birth new stars gets consumed, locked away inside stellar remnants, or spread too thin across an ever-expanding universe to collapse into anything new. Galaxies themselves will not persist unchanged either. Over spans of time stretching far beyond anything currently observed, individual stars within a galaxy will gradually be flung outward through gravitational interactions with their neighbors, drifting off into the ever emptier space between galaxies, while other stars fall inward and are eventually consumed by the supermassive black hole lurking at their galaxy's center. Given enough time, Every galaxy is expected to lose the vast majority of its stars this way, either scattered outward into the growing darkness or swallowed entirely by their own central black hole, a slow, patient process of dissolution that will eventually leave the universe populated mostly by isolated black holes drifting through emptiness, themselves slowly losing mass over an even longer span of time through an extraordinarily slow quantum process, theorized by physicist Stephen Hawking, in which black holes very gradually radiate away their own mass until nothing remains of them at all. The final state predicted by this long, patient unraveling is a universe filled with nothing but a diffuse, thin scattering of subatomic particles and radiation, spread so evenly and so thinly across an unimaginably vast, cold, and continuously expanding space that no meaningful structure, no stars, no planets, and certainly no life of any kind could ever exist within it again. Physicists refer to this ultimate scenario using a name that captures its essential quality without any need for embellishment, calling it simply the heat death of the universe. A state defined not by any dramatic destructive event, but by the complete and permanent absence of any remaining energy gradient, capable of doing anything at all, forever. Even setting aside this distant future, there remains a more immediate and, in some ways, more disorienting horror connected to the very edge of what current instruments can observe at all. The observable universe extends outward in every direction to a boundary roughly 93 billion light-years across, a figure that already sounds staggering, but the reason behind that number is stranger than the number itself. Because the universe has been expanding this entire time, the light reaching us today from the most distant visible objects left its source when the universe was very young, and that source has since been carried much farther away by the ongoing expansion of space itself. We are, in effect, looking at a fossilized image of extremely distant regions as they existed billions of years ago, with no way of knowing directly what has happened to them since any light describing their current state has not yet had time to reach us, and, given the accelerating expansion discussed earlier, some of it never will. Beyond this observable boundary, scientists have no direct way of confirming what exists at all. The overwhelming consensus among cosmologists holds that the universe almost certainly continues far beyond what we can currently see, likely following the same basic physical laws observed within our own observable patch, simply because there is no compelling reason within current physics to expect our particular vantage point to sit at any special edge or boundary. But this remains, fundamentally, an assumption built on reasonable extrapolation rather than direct evidence, since the region beyond our cosmic horizon is, by definition, permanently inaccessible to any observation we could ever perform, no matter how advanced our instruments eventually become. Some cosmological models go further still, proposing that our entire observable universe might represent only a vanishingly small patch within an unimaginably larger structure, sometimes described using the term multiverse, where other equally vast regions exist beyond our own, potentially governed by different physical constants or even fundamentally different laws of physics altogether. These ideas remain firmly in the realm of theoretical speculation, difficult or perhaps even impossible to test directly, given that any such region would, again by definition, lie forever beyond anything we could ever observe or measure. Yet the mathematics underlying several of our most successful physical theories, models that have otherwise proven remarkably accurate in describing the universe we can measure, naturally suggest the plausibility of exactly this kind of vastly larger structure, leaving physicists in the uncomfortable position of taking the idea seriously without any realistic path toward confirming or ruling it out through direct evidence. This is, in its own quiet way, perhaps the most complete horror this entire outward journey ultimately arrives at. It is not a horror built from cold or radiation or crushing gravity or even the slow, patient decay awaiting the universe across trillions of years. It is the recognition that no matter how far outward this journey travels, whether by spacecraft, by telescope, or simply by careful mathematical reasoning, there remains a hard boundary built into the very structure of observation itself, beyond which nothing can ever be confirmed, only guessed at using whatever patterns happen to hold true within the small, temporary, and increasingly isolated patch of universe we happen to occupy. Scattered throughout the galaxy, and indeed throughout every galaxy astronomers have studied, lies a category of star that never quite managed to become a star at all in the traditional sense. Brown dwarfs form the same way ordinary stars do, from a collapsing cloud of gas and dust pulled together by gravity, but they simply never accumulate quite enough mass to ignite the sustained nuclear fusion of hydrogen that powers stars like our Sun. Instead, they smolder rather than shine, radiating away the residual heat left over from their formation, glowing dimly in infrared light rather than the visible spectrum, cooling slowly over billions of years without ever reaching the sustained thermonuclear ignition that would make them true stars. These failed stars occupy a strange middle ground between planet and star, some barely larger than Jupiter, and others many times more massive, yet none of them producing the steady, long-lived warmth of an actual sun. A planet orbiting a brown dwarf, should one exist, would receive so little usable light and heat that maintaining anything resembling a stable, temperate surface would require an almost impossibly precise and narrow orbital distance, one that itself would only remain viable for a limited stretch of time, as the brown dwarf continued cooling and dimming further with each passing million years. Astronomers have identified brown dwarfs scattered throughout the solar neighborhood, some drifting closer to our own sun than many stars. Silent and nearly invisible companions occupying the dark spaces between the brighter, more familiar points of light filling our night sky. Because brown dwarfs emit so little visible light, they remained essentially undetectable until relatively recently in the history of astronomy. And even now, many almost certainly drift undiscovered throughout the galaxy, their faint infrared glow lost against the background noise of a much brighter universe. A traveler passing near an undiscovered brown dwarf might receive no advance warning of its presence at all, its gravity announcing itself only through subtle effects on nearby objects long before any telescope could actually resolve the object directly. In this sense, brown dwarfs represent a quieter cousin to the rogue planets discussed earlier in this journey, another category of massive, cold, nearly invisible object populating the supposedly empty spaces between the stars we can actually see and name. Some of the coldest brown dwarfs discovered so far have surface temperatures low enough to overlap with the range found on some planets, cool enough that scientists studying their atmospheres have detected the signatures of water clouds forming directly within them, an almost surreal detail for an object that technically began its existence as a failed star rather than a planet. This blurred boundary between star and planet is itself an unsettling reminder that the universe rarely respects the tidy categories used to describe it, and that traveling far enough outward inevitably means encountering more and more objects that defy easy classification entirely, each one adding its own quiet, cold, and largely unstudied hazard to the growing list of things a traveler moving through deep space must account for. Among the most violent events observable anywhere in the universe are gamma-ray bursts, brief but extraordinarily intense flashes of high-energy radiation, believed to originate from the collapse of certain massive, rapidly rotating stars, or, from the merger of two neutron stars, similar to those discussed earlier in this journey. In the span of just a few seconds, a single gamma-ray burst can release more energy than our own sun will produce across its entire multi-billion-year lifetime, a scale of destructive potential that is difficult to overstate. If a gamma-ray burst occurred within our own galaxy and happened to be aimed directly at Earth, the resulting radiation could potentially strip away a significant portion of the planet's protective ozone layer, exposing surface life to dramatically increased levels of ultraviolet radiation and potentially triggering a mass extinction event, an idea some scientists have seriously proposed as a possible explanation for at least one major extinction recorded in Earth's ancient geological history. The narrow, focused beams of radiation produced by these events travel across the galaxy essentially unimpeded, meaning a gamma-ray burst, originating from a star system many thousands of light-years away, could still deliver a dangerous dose of radiation to anything unlucky enough to lie directly within its narrow beam, a beam that itself might be only a few degrees wide, meaning most gamma-ray bursts miss Earth entirely, simply due to the geometry of the universe, rather than any protective mechanism at play. A traveler stationed anywhere within the galaxy faces this hazard as an ever-present, essentially unpredictable background risk, one that current instruments can only detect after the fact, once the burst of radiation has already arrived and been measured, offering no meaningful advance warning capable of allowing evasive action of any kind. This unpredictability is itself part of what makes gamma-ray bursts such a uniquely unsettling hazard compared to almost everything else described so far in this journey. Radiation belts around Jupiter, the cold of the Kuiper Belt, the crushing gravity near a black hole, all of these are hazards that can be mapped, predicted, and planned around with reasonable confidence using known physics and careful observation. A gamma-ray burst offers none of that certainty. It can, in principle, originate from a star system that showed no obvious signs of instability just moments before the event, striking a target many thousands of light-years away with essentially no warning, a reminder that even regions of space that appear calm and well understood based on decades of careful observation can, without any notice at all, become the source of an event capable of reshaping the biosphere of a distant, otherwise unrelated planet. Fortunately for life on Earth, current models suggest the odds of a sufficiently close and precisely aimed gamma-ray burst occurring within any given million-year window remain relatively low, and no such event has struck our planet directly within recorded human history. But zoom out across the full lifetime of a galaxy, spanning many billions of years, and the odds shift considerably, meaning that any civilization surviving long enough within a single galaxy will very likely, sooner or later, contend with at least one such event somewhere within its stellar neighborhood, whether or not it happens to be pointed directly at their own particular world. Underlying every single hazard described throughout this entire journey sits a mystery so fundamental that scientists still cannot say with certainty what makes up the majority of the universe at all. Careful measurements of how galaxies rotate, how galaxy clusters bend, passing light, and how the earliest structure of the universe formed all point toward the existence of something scientists call dark matter, a form of matter that does not emit, absorb, or reflect light in any way, and has never been directly detected by any experiment, despite decades of dedicated searching using extraordinarily sensitive instruments buried deep underground, specifically to shield them from other sources of interference. And yet, according to the best current measurements, this invisible material outweighs all the ordinary matter making up stars, planets, and everything discussed throughout this entire journey by a significant multiple. This means that every star, every planet, every black hole, And every rogue world encountered throughout this outward journey represents only a small fraction of the total mass actually present in the universe, with the majority existing as something fundamentally unknown, detectable only through its gravitational influence on the ordinary matter we can actually observe directly. A traveler moving through what appears to be empty interstellar or intergalactic space is, according to current physics, actually moving through a sea of this invisible material the entire time, gravitationally significant, yet completely undetectable by any instrument built so far. An invisible scaffolding underlying the entire visible structure of the cosmos, without ever revealing what it actually is. Dark energy compounds this uncertainty even further. The mysterious force responsible for the accelerating expansion of the universe discussed earlier in connection with the cosmic horizon appears, according to current measurements, to account for an even larger share of the total energy content of the universe than either ordinary matter or dark matter combined. Scientists can measure its effects with impressive precision, tracking exactly how it accelerates the expansion of space across cosmic history, yet its fundamental nature remains almost entirely unknown, described mathematically, using a term added to Einstein's equations of general relativity, but lacking any deeper physical explanation that has achieved anything close to scientific consensus. Taken together, these two mysteries mean that everything encountered throughout this entire journey, every planet, every star, every black hole, every galaxy, and every void, represents only a small, visible fraction of what the universe actually contains, with the vast majority of its total mass and energy existing in forms current physics still cannot directly explain or detect. This is perhaps the quietest and most persistent horror underlying this entire outward journey. It is not a hazard a traveler could encounter directly, the way radiation or extreme cold might be encountered. It is the unsettling recognition that the universe being explored, mapped, and measured throughout this entire journey remains, even now, mostly invisible, mostly unexplained, and mostly beyond the reach of current scientific understanding. No matter how far outward any future journey manages to travel far enough outward, and eventually the journey stops moving through space entirely and starts moving backward through time itself, arriving at the faint, ancient afterglow of the universe's own birth. The cosmic microwave background is radiation left over from a period roughly 380,000 years after the Big Bang, when the universe first cooled enough for light to travel freely, rather than being constantly scattered by a hot, dense fog of charged particles. This radiation fills the entire sky in every direction, arriving from every direction simultaneously. A faint microwave glow measured with extraordinary precision by orbiting telescopes designed specifically to map its subtle variations in temperature across the sky. Those subtle variations, differences of only a tiny fraction of a degree from one point in the sky to another, represent the earliest seeds of all the structure that would eventually form throughout the universe. The faint gravitational imprints that would, over billions of years, grow into the galaxies, stars, and planets filling the cosmos we observe today. Studying this ancient light in detail has allowed cosmologists to determine the age, composition, and geometry of the entire observable universe with remarkable precision, confirming many of the details discussed throughout this journey regarding dark matter, dark energy, and the overall structure and history of everything that exists. And yet, this ancient light also represents an absolute wall beyond which no further direct observation using light is possible at all. Before that moment, roughly 380,000 years after the Big Bang, the universe was filled with a hot, opaque plasma that scattered light constantly, meaning no photon from that earlier era could ever travel freely enough to reach any telescope, no matter how sensitive or how patiently it observed the sky. Everything that happened during the universe's earliest moments, the period scientists call inflation, along with whatever process caused the Big Bang itself, remains permanently hidden behind this wall of ancient light, accessible only through indirect theoretical reasoning and mathematics, rather than any direct observation that could ever be performed. This means that even traveling backward through time using light, rather than forward through space using a spacecraft, eventually reaches its own absolute limit, a boundary built into the very physics of how light and matter interacted during the universe's hot, dense infancy. Whatever occurred before this boundary, whatever truly caused the Big Bang, whatever conditions existed in that first fraction of a second, remains and will likely always remain beyond any possibility of direct confirmation, a final, permanent horizon layered on top of every other horizon already encountered throughout this journey, reminding any traveler, however far they manage to travel, that some questions about the universe may never receive an answer built from anything more solid than careful, educated speculation. There is one more silence worth confronting before this journey turns back toward home. A silence that has troubled scientists for decades, precisely because it should not, by most reasonable calculations, exist at all. Given the sheer number of stars in our galaxy alone, a number reaching into the hundreds of billions, and given how many of those stars are now known to host planets of their own, a fact confirmed repeatedly by orbiting telescopes designed specifically to detect them, the statistical odds of intelligent life having arisen somewhere else within the galaxy seem, to many scientists, uncomfortably favorable. And yet, despite decades of careful listening using radio telescopes built specifically for this purpose, no confirmed signal from any other civilization has ever been detected, anywhere, at any time. This contradiction has a name: the Fermi paradox, after the physicist who is said to have first posed the question informally during a conversation with colleagues, asking simply where everybody is, given how likely intelligent life seemed to be based on the numbers involved. Decades later, that question remains entirely unanswered, and the proposed explanations range from the comforting to the deeply unsettling. Perhaps intelligent life is simply far rarer than the raw numbers suggest, requiring a chain of extraordinarily unlikely conditions that happen to align only once here on Earth. Perhaps civilizations do arise elsewhere, but tend not to survive very long once they develop the technology capable of sending detectable signals, undone by threats either environmental or of their own making, before they ever manage to make meaningful contact with anyone else. Other proposed explanations lean even further into unease. Some researchers have suggested that advanced civilizations might deliberately choose to remain silent, aware that broadcasting their location and existence to the wider galaxy could carry risks they consider unacceptable, a strategy sometimes referred to as the dark forest hypothesis, borrowed from a work of speculative fiction but taken seriously by at least some scientists studying the question. Under this reasoning, the galaxy's silence would not indicate emptiness at all, but rather a universe filled with civilizations that have each independently concluded that staying quiet is safer than announcing themselves to whatever else might be listening in the dark. Whatever the true explanation eventually turns out to be, the silence itself becomes more unsettling the further this journey has already traveled. Everything discussed so far, the radiation, the cold, the crushing gravity, the accelerating expansion, the invisible majority of the universe's own mass, all of it describes a cosmos that is, by any reasonable measure, extraordinarily vast and extraordinarily old. A universe this large and this old should, statistically, be a noisy place, filled with the signals and structures of countless other civilizations that arose long before or alongside our own. Instead, every direction we have ever pointed an instrument has returned the same simple, consistent answer: silence, an absence of evidence that becomes, the longer it persists and the further we look, its own distinct and deeply unsettling kind of discovery. Bring this entire journey back to its beginning, and a clear pattern becomes impossible to ignore, one that answers the question this journey set out to explore in the first place. Space does not become gradually more dangerous the farther you travel in some smooth, predictable curve. It becomes dangerous in distinct, escalating stages, each one revealing a category of hazard the previous stage had not yet introduced. Near Earth, the danger is temperature and vacuum and radiation. All things a sufficiently thick suit or hull can, at least partially, hold back. Cross into interplanetary space, and the danger becomes accumulation, a slow, patient damage, building across months of exposure to particles no shielding can fully stop. Cross into the outer solar system, and the danger becomes darkness and isolation so complete that rescue itself becomes a meaningless concept. Cross into interstellar space, and the danger becomes time itself, generations passing aboard a ship while decades or centuries pass without it. Cross into intergalactic space, and the danger becomes scale so vast that light, the fastest thing that exists, cannot finish a message before the universe forgets what it was ever asking. And cross far enough into the future, or against the very edge of the observable universe, and the danger stops being anything a traveler could survive or avoid at all, becoming instead a simple, permanent limit on what can ever be known. What makes this progression so unsettling is not any single hazard within it. Radiation belts, extreme cold, crushing gravity, and generational isolation are each, on their own, comprehensible dangers. The kind that engineers and scientists can study, measure, and plan around with reasonable confidence. What makes the full progression unsettling is the pattern itself. The way each new threshold crossed reveals that the universe was hiding an even larger, even more indifferent scale of hazard just beyond the one already understood. Earth's atmosphere hides the true intensity of solar radiation. The heliosphere hides the true intensity of galactic cosmic rays. Our own galaxy's relatively quiet neighborhood hides the true violence found closer to its center. And the observable universe itself hides, by definition, whatever lies beyond it, a boundary rather than an edge, one this journey can approach conceptually but never actually reach. There is something almost humbling buried within this realization. Once the fear of it settles into something closer to perspective, every hazard cataloged throughout this journey exists because the universe operates according to consistent, discoverable physical laws. Laws that allowed scientists working from a single, small, temperate planet to calculate the temperature of a moon they had never visited, to predict the existence of a black hole decades before ever photographing one directly, and to measure the age of light that began traveling before our own planet had even finished forming. The same universe capable of producing conditions this extreme and this indifferent to survival is also, somehow, comprehensible enough that a species confined to one small world could work out so much of how it actually operates, using nothing more than careful observation, patient mathematics, and an enormous amount of curiosity extended safely from the comfort of home. That comfort is worth pausing on directly, because it is easy, after a journey like this one, to overlook just how narrow and how fortunate the conditions supporting it actually are. Earth sits at almost exactly the right distance from a stable, long-lived star. It carries a magnetic field strong enough to deflect the worst of what that star and the wider galaxy throw at it. It holds an atmosphere thick enough to insulate against the temperature swings that make the Moon and Mars so unforgiving, while remaining thin enough to let sunlight through rather than trapping heat the way a runaway greenhouse effect eventually will on a world like Venus. None of these conditions were guaranteed, and none of them are permanent. But for the narrow slice of cosmic time we currently occupy, they hold, offering a rare and quiet exception to almost everything else this journey has revealed about the wider universe surrounding it. It is worth remembering, too, that this same universe capable of producing black holes and vanishing galaxies has already demonstrated its indifference far closer to home than any of the distant destinations covered throughout this journey. In 1859, a solar storm now known as the Carrington event struck Earth directly, a burst of charged particles so intense that telegraph operators around the world reported sparks leaping from their equipment. And auroras, normally confined to polar regions, were seen as far south as the Caribbean. At the time, the world's electrical infrastructure consisted of little more than telegraph wires, and the damage, while dramatic, remained limited largely to that single, relatively simple technology. A storm of comparable intensity striking Earth today would interact with a civilization built almost entirely around electricity, satellites, and interconnected digital communication, none of which existed in any form during the 19th century. Engineers who have studied this scenario in detail warn that a modern Carrington-level event could induce damaging electrical surges across long-distance power transmission lines, potentially destroying large transformers that, in some cases, take many months to manufacture and replace, leaving affected regions without reliable electricity for an extended period while replacement equipment is built and installed. Satellites in orbit would face their own separate danger, exposed directly to intensified radiation and charged particles without the protective shielding of Earth's thick atmosphere, potentially damaging navigation, communication, and weather monitoring systems that modern life depends on in ways most people rarely stop to consider. Scientists monitoring the sun have identified numerous events throughout history and prehistory using indirect evidence preserved in tree rings and ice cores, evidence of solar storms considerably more intense than the Carrington event. Some occurring in the centuries before recorded history could describe them directly. This evidence suggests that events of this scale, while rare on the timescale of an individual human life, are not nearly rare enough on the timescale of a civilization expected to persist for centuries or millennia, meaning a storm capable of seriously disrupting modern infrastructure remains a matter of eventual probability rather than remote, theoretical possibility. The sun that provides the warmth and light making life on Earth possible in the first place is, in this sense, the very same indifferent, unpredictable star discussed earlier in connection with the more violent behavior of smaller red dwarf stars, simply operating at a gentler, though still occasionally dangerous, baseline. This is, perhaps, the most important reminder this entire journey outward has to offer. The line between a peaceful, stable home and a hostile, unpredictable universe was never as firm as it might feel on an ordinary day. It is a matter of degree rather than a matter of kind. The same physics producing gentle sunlight and devastating stellar storms, the same gravity holding the Earth in a stable orbit and stretching unlucky matter apart near a black hole, the same vast ancient universe that allowed life to arise here at all, and that will, eventually, continue on in some form long after every star currently visible in the night sky has gone quiet. Closer still to home, the same solar system that hides black holes, magnetars, and rogue planets in its farthest reaches also holds a far more immediate and statistically certain hazard, one that has already shaped the history of life on Earth more than once. Asteroids and comets continue to cross Earth's orbital path on a regular basis, and while the overwhelming majority pass by harmlessly at distances, astronomers track with great precision. The geological record makes clear that direct impacts have occurred before and will occur again. The event believed to have ended the age of the large dinosaurs roughly 66 million years ago is now attributed, with strong supporting evidence, to an asteroid measuring roughly 10 kilometers across, striking what is now the coast of Mexico. An impact that released energy equivalent to billions of the most powerful weapons ever built by humans, triggering global wildfires, tsunamis, and a period of prolonged darkness as debris blocked sunlight for months, disrupting the food chain so severely that the majority of species alive at the time did not survive the aftermath. Objects of this size, fortunately, are rare, and astronomers have already cataloged the vast majority of the largest, most dangerous near-Earth asteroids, none of which currently show any trajectory that would bring them into direct contact with our planet within the foreseeable future. Smaller objects present a subtler challenge, precisely because they remain far more numerous and far harder to detect in advance. In 1908, an object believed to be a small asteroid or fragment of a comet exploded in the atmosphere above a remote region of Siberia, flattening an area of forest spanning more than 2,000 square kilometers, with an airburst powerful enough to be felt hundreds of kilometers away, despite the object itself never actually reaching the ground intact. Had that same event occurred above a densely populated city rather than a sparsely inhabited forest, the resulting loss would have been severe. A sobering reminder that meaningful impact events remain possible on timescales considerably shorter than the many millions of years separating major extinction-level impacts. Space agencies have begun taking this hazard seriously enough to test active countermeasures rather than relying solely on early detection and evacuation planning. In a mission conducted in recent years, engineers deliberately guided a spacecraft into collision with a small asteroid moon, successfully altering its orbital period by a measurable amount and confirming, for the first time, that a kinetic impact strategy could realistically deflect a hazardous object given sufficient advance warning. This success represents genuine progress, but it also depends entirely on detecting a threatening object with enough lead time to plan and execute a deflection mission, a requirement that remains far from guaranteed given how many smaller, harder-to-detect objects continue to be discovered only after they have already passed dangerously close to Earth. The lesson embedded in this particular hazard differs slightly from everything else covered throughout this journey, because it is the one danger discussed here that a civilization confined entirely to its home planet has genuine, demonstrated power to address directly, given enough advance warning, enough coordinated effort, and enough patience to fund and maintain detection systems across the many quiet decades between actual close calls. Every other hazard covered in this journey, the radiation, the cold, the crushing gravity, the vanishing galaxies, exists at a scale so far beyond direct human intervention that survival depends entirely on avoidance, shielding, or simply choosing not to travel far enough to encounter it. This one, uniquely, offers something closer to genuine agency, a reminder that not every cosmic hazard needs to remain purely something to fear from a distance. Venus offers one final, uncomfortable reminder that a planet does not need to be far away at all to qualify as one of the most hostile environments encountered throughout this entire journey. It orbits closer to the Sun than Earth does, and at first glance, similar in size and composition to our own world, it might seem like the more obvious candidate for life compared to the cold, thin deserts of Mars. Instead, Venus experienced what scientists describe as a runaway greenhouse effect, a process in which its thick atmosphere, composed overwhelmingly of carbon dioxide, trapped heat so effectively that its surface temperature climbed to roughly 460 degrees Celsius, hot enough to melt lead, and remains that hot consistently, day and night, across the entire planet, with no meaningful variation between its sunlit and shaded regions at all. The atmospheric pressure at Venus's surface compounds this heat into something even more punishing, reaching roughly 90 times the pressure found at sea level on Earth, comparable to the crushing pressure found nearly a kilometer beneath the surface of Earth's oceans. Spacecraft sent to land on Venus have survived only briefly, in some cases functioning for less than 2 hours before the combination of extreme heat and crushing pressure disabled their systems entirely. A striking contrast to landers sent to Mars, some of which have continued operating for years. Clouds high in Venus's atmosphere are composed largely of sulfuric acid, adding a corrosive hazard on top of the heat and pressure, one that has forced engineers designing any future mission to the planet's surface to consider materials and protective coatings capable of withstanding a chemical environment unlike almost anywhere else studied so far in this journey. What makes Venus particularly unsettling within the context of this entire outward journey is how ordinary its starting conditions likely were. Current models suggest Venus may once have had a more temperate climate, potentially even liquid water on its surface, before a combination of its proximity to the Sun and a runaway feedback loop involving its own atmosphere transformed it permanently into the hostile world observed today. If this model holds, Venus represents proof that a planet does not need any dramatic external event, no asteroid impact, no nearby supernova, no wandering rogue star, to become lethally hostile. Sometimes a world simply crosses a threshold in its own atmospheric chemistry, quietly and gradually, until conditions that once might have supported life become instead conditions capable of destroying almost any spacecraft sent to study them directly. This detail sits close enough to home that it deserves particular attention within a journey otherwise focused on the farthest, coldest, and most extreme regions of the universe. Venus is, by cosmic standards, practically next door. A close planetary neighbor sharing roughly the same birthplace and roughly the same raw materials as Earth itself. And yet, it stands today as one of the most uniformly lethal surfaces in the entire solar system. A quiet warning that hostility in this universe does not always require distance at all. Sometimes it only requires time, and the wrong set of atmospheric conditions compounding on themselves, slowly, until an entire world tips past the point where anything resembling the familiar could ever survive there again. There is a strange comfort hidden inside all of this, one that only becomes visible once the full scale of the journey has been laid out from beginning to end. Every hazard described throughout this journey, from lunar vacuum to the crushing gravity near a supermassive black hole, from the accelerating expansion carrying entire galaxies beyond reach to the invisible majority of the universe's own mass, exists because the cosmos operates according to physical laws precise enough to be measured, modeled, and in many cases predicted decades before direct confirmation ever arrived. Nothing described throughout this journey is arbitrary or capricious in the way certain kinds of danger can feel on a much smaller, human scale. Every threshold crossed, from the moon outward to the very edge of the observable universe, follows directly from consistent principles that a small number of curious, patient scientists, working from a single, modestly sized planet, managed to work out using nothing more than careful observation, rigorous mathematics, and an enormous amount of stubborn persistence extended across generations of research. That consistency is, in its own way, the closest thing to reassurance this particular journey has to offer. The universe is not hunting for us specifically. It does not distinguish between a fragile, curious species and an inert rock when a solar storm erupts, or when a stray hydrogen atom strikes a hull at relativistic speed, or when a gravitational wave passes silently through everything in its path. The hazards cataloged throughout this journey are simply the ordinary, indifferent behavior of a universe operating exactly as its own physics dictates. Everywhere, at every scale, all at once, whether or not anything capable of noticing happens to be present to observe it. Earth's particular safety, narrow and temporary as it may ultimately prove to be, is not an exception carved out from that indifference. It is simply the result of a very specific, very fortunate set of local conditions, holding steady for exactly as long as they have been needed. Understanding this changes the emotional weight of everything covered throughout this entire outward journey, at least a little. The moon's airless cold, the crushing radiation belts surrounding Jupiter, the patient stretching of a body falling toward a black hole's event horizon, the slow cooling of a star toward its eventual black dwarf state trillions of years from now. None of these facts were designed with any traveler in mind, human or otherwise. They are simply what happens, consistently and predictably, given the physical conditions present at each particular location and each particular moment in time. There is something almost steadying in that consistency. A reminder that the universe's vast indifference is not the same thing as malice, and that the same careful reasoning capable of predicting a hazard from a great distance is often also capable of finding a way to survive it, given enough preparation and enough respect for what the numbers are actually saying. And so this journey, having traveled from the airless cold just beyond Earth's atmosphere all the way out toward the permanent, receding edge of everything that can ever be observed, ends not with a warning to stay home forever, but with a clearer, more honest picture of exactly what waits beyond the door before anyone chooses to open it. Space does become more extreme the farther you travel, in nearly every measurable sense: more radiation, more cold, more isolation, more time distorted beyond recognition, and eventually, more silence than any single mind can comfortably hold. But it also becomes more understandable with every mission flown, every instrument launched, and every careful measurement returned. A universe that reveals more of its true, strange nature exactly in proportion to how far anyone is willing to travel to meet it. Occasionally, the wider hazards of interstellar space do not wait for a traveler to leave home at all, arriving instead as brief, uninvited visitors passing directly through our own solar system. In 2017, astronomers detected an object moving through our solar system on a trajectory that made clear it had originated from beyond our sun entirely, the first confirmed interstellar object ever observed passing through our own cosmic neighborhood. It moved too fast, and along a path too sharply curved to have originated anywhere within our own solar system, meaning it had spent an unknown, likely enormous stretch of time drifting alone through interstellar space, quite possibly for many millions of years, before its path happened to intersect briefly with the region we call home. This object displayed a strange, elongated shape, unlike most asteroids or comets typically observed within our own solar system. And it also showed a subtle, unexpected acceleration as it departed, a small extra push beyond what gravity alone could explain. Scientists proposed several natural explanations for this behavior, most centering on the gentle outgassing of trace amounts of frozen material, vaporizing as the object passed near the sun, similar to the process that produces a comet's visible tail, though in this case too faint to be directly observed, given the object's small size and unusual composition. A small minority of researchers raise the more speculative possibility that the object's unusual shape and motion might indicate an artificial origin, a hypothesis that generated significant public attention despite remaining, among the majority of the scientific community studying the object, a distant, unproven possibility rather than a leading explanation. Since that first detection, astronomers have identified additional interstellar visitors passing through our solar system, confirming that objects originating from other star systems drift through our own cosmic neighborhood far more regularly than anyone had previously confirmed through direct observation. Each of these objects represents a genuine, physical sample of material formed around an entirely different star, shaped by processes and conditions that occurred light years away and, in some cases, potentially billions of years before our own sun and planets ever began to form. A traveler intercepting one of these objects directly would be touching material older than Earth itself, carried across a distance and duration that make even the vast solar system explored throughout most of this journey feel, by comparison, remarkably small and remarkably young. What makes these interstellar visitors particularly unsettling is simply how little warning accompanies their arrival. Each of the confirmed interstellar objects detected so far was discovered only after it had already entered our solar system, moving on a trajectory that gave astronomers mere weeks or, at best, a few months to study it before it departed again, continuing outward on a path that will likely carry it beyond any telescope's reach for the remainder of its existence. There is no way, using current detection methods, to predict the arrival of the next interstellar visitor in advance, meaning our solar system remains open at every moment to brief, unplanned encounters with material and objects that originated somewhere else entirely, arriving without warning and departing again just as quickly, carrying whatever secrets they hold back out into the same vast interstellar darkness this journey has already spent so long exploring. Even the icy moons scattered throughout the outer solar system, discussed earlier, mostly in terms of radiation and cold, hide a further layer of hazard buried beneath their frozen surfaces. Saturn's small moon Enceladus has been observed venting enormous plumes of water vapor and ice particles from cracks near its southern pole, geysers powerful enough to be detected directly by passing spacecraft, confirming the presence of a liquid ocean hidden beneath many kilometers of solid ice. This ocean is kept liquid, not by any warmth from the distant sun, but by the same tidal flexing that drives volcanic activity on Io, the moon's interior repeatedly stretched and squeezed by Saturn's powerful gravity as it follows its slightly irregular orbit, generating enough internal friction to maintain liquid water despite surface temperatures cold enough to freeze nearly every other substance solid. A traveler attempting to explore this hidden ocean directly would need to descend through many kilometers of solid ice under crushing pressure, without any guarantee of finding a stable path downward, since the exact thickness and structure of that ice shell remains only partially understood even after multiple spacecraft have studied the moon directly. Should a submersible eventually reach the ocean itself, it would be exploring a liquid environment in complete and permanent darkness, cut off from sunlight by an ice shell far too thick for any usable light to penetrate, relying entirely on artificial illumination and whatever heat sources exist naturally on the ocean floor, similar in principle to the volcanic vents supporting isolated ecosystems in Earth's own deep oceans. Whether any form of life exists within these hidden oceans remains one of the most tantalizing open questions in modern planetary science, and it is a question that carries its own quiet unease. If life does exist there, it would have evolved in complete isolation from sunlight, from Earth, and from anything resembling the conditions that shaped life on our own planet, developing along a path entirely disconnected from everything we currently understand about biology. And if no life exists there, despite conditions that appear, on paper, reasonably favorable, that absence would raise its own uncomfortable question about just how rare the specific chain of circumstances that produced life on Earth actually turns out to be. Adding one more layer of uncertainty to a universe that, the farther this journey has traveled, has offered surprisingly few clear answers and surprisingly many new, deeper questions in their place. Think back, for a moment, to everything this journey has actually covered. It began just beyond Earth's own doorstep, on a dead, airless moon, where a single unprotected breath in vacuum would end consciousness within seconds. It moved through the radiation-soaked emptiness between planets, where the same cosmic rays that occasionally streak harmlessly through your own body right now would, given enough unshielded exposure across many months, quietly rewrite the genetic code of anyone traveling toward Mars. It crossed a belt of scattered rubble, far emptier than fiction ever admits, then pushed outward past gas giants wrapped in radiation belts capable of frying a spacecraft's electronics within hours, past ice giants howling with winds faster than anything ever recorded on Earth, and out into a frozen, twilight region where the sun itself finally stops behaving like a source of daylight at all. From there, this journey crossed into a darkness so complete that a signal sent home would take years, then decades, then centuries just to arrive. Following a spacecraft already older than most living memory, as it drifted towards stars so distant that reaching them at all would mean surrendering entire human lifetimes. Generations born and raised without ever seeing the world their ancestors once called home. It passed neutron stars dense enough to compress a mountain into a teaspoon, rogue planets wandering forever without a star to warm them, and a supermassive black hole at the center of our own galaxy, massive enough to stretch anything that strayed too close until it could no longer hold its own shape together at all. And then, this journey kept going, past our own galaxy entirely, into a void so empty that entire regions of the sky would eventually fade into near total darkness, toward a cosmic horizon that recedes exactly as fast as anything can approach it, carrying countless galaxies permanently beyond any possibility of contact, some of them already gone by any meaningful definition, their final fate forever unknown and unknowable to us. It reached forward across trillions of years toward a universe destined to cool, dim, and empty itself entirely. And it reached backward across billions of years toward the faint, ancient light of the universe's own infancy, a wall beyond which no telescope will ever see, no matter how long it waits or how patiently it watches. Through all of that vast, cold, indifferent distance, one thing became clearer with every single threshold this journey crossed. The farther you travel, the more the universe reveals just how narrow, how fragile, and how genuinely remarkable it is that anything capable of understanding all of this exists at all. Here, on one small, temperate world, orbiting one small, stable star, protected by one modest magnetic field and one thin, forgiving layer of atmosphere, all of it holding steady for exactly as long as it has been needed, and not one moment longer than that. Every hazard cataloged throughout this journey is real, measured, and waiting exactly where the physics says it should be. But so is the quiet, improbable fact that a species born on that one small world managed to work out where all of it is, how it behaves, and roughly what it means, using nothing more than curiosity, patience, and the willingness to keep looking outward, no matter how unsettling the answers eventually became. If this journey through the widening horror of deep space left you with a new appreciation for exactly how much stands between you and the cold, radiation-soaked emptiness surrounding this one quiet planet, Consider staying with us for more of these journeys into the cosmos, and take a moment now to like this video and subscribe, so the next expedition into the strange, vast, and indifferent universe finds its way to you as well. For now, though, the journey outward is finished. Let the distance you have just traveled settle quietly into the back of your mind, and let this small, sheltered corner of the universe hold you exactly where you are. Close your eyes if it helps. Let your breathing slow, one gentle breath after another. Somewhere far above you, that same vast, ancient darkness is still stretching outward in every direction it has always stretched, patient and indifferent, exactly as it has for billions of years, and exactly as it will for trillions more. But here, for now, everything remains still and quiet and safe. Rest now, and let the universe drift on without you for a while.